Imagine two twins. One stays on Earth, the other boards a spaceship, travels to a distant star at nearly the speed of light, and returns home. When the traveling twin returns, something strange has happened. The traveler is younger than the twin who stayed home, years or even decades younger. This is the famous twin paradox, and for over a century it has confused students, sparked debates, and even led some to question whether Einstein was wrong. But here is the truth. There is no paradox at all. The apparent contradiction disappears once you understand one crucial detail that most popular explanations get wrong. Welcome to Großdenken, my friends. Today, we are going to explain what the twin paradox really is, why it is not a paradox, and exactly why one twin actually ages less. Please support this channel grow by just subscribing. That would mean a great help. First, let us understand why this seems like a paradox. According to special relativity, time dilation is symmetrical. If you are moving relative to me, I see your clock running slow, and you see my clock running slow. So here is the problem. From the Earth twin's perspective, the spaceship is moving. So the traveling twin's clock should run slow. The traveler should return younger. That matches the prediction. But from the traveling twin's perspective, the Earth is moving away at the same speed. So the Earth twin's clock should run slow. That means the Earth twin should be the younger one. Both perspectives seem equally valid. So which one is right? They cannot both be right. That is the paradox. This apparent contradiction has led some people to claim that special relativity is inconsistent. But Einstein was not wrong. The resolution lies in a key fact that breaks the symmetry. Here is the crucial detail that most people miss. For the twins to compare their ages, they must be in the same place at the same time. The traveling twin has to turn around and come back. That turn involves acceleration. The Earth twin never accelerates, the traveling twin does. This acceleration breaks the symmetry between the two twins. In the language of relativity, the Earth twin remains in a single inertial frame, a frame moving at constant velocity. The traveling twin changes frames during the turnaround. Special relativity applies perfectly to inertial frames, but the traveling twin is not in a single inertial frame for the whole journey. Because the situation is not symmetric, there is no requirement that the twins age the same amount. The traveling twin will return younger. This is not just a thought experiment. The twin paradox has been confirmed by real experiments. The most famous is the Hafele-Keating experiment in 1971. Scientists flew atomic clocks around the Earth on commercial airplanes, one eastward, one westward, while comparing them to reference clocks on the ground. The clocks on the eastward trip, moving in the direction of Earth's rotation, ran slower than the ground clocks. The clocks on the westward trip ran faster. The results matched the predictions of both special and general relativity to within experimental uncertainty. Even more dramatic, muons accelerated to nearly the speed of light. In storage rings at CERN experienced accelerations 10 to 18 times Earth's gravity. And their decay times were extended exactly as relativity predicts, confirming that acceleration does not directly affect clock rates. The twin paradox is not theoretical, it is measured physics. Here is where many explanations get it wrong. You will often hear that acceleration causes time dilation. That is not correct. Experiments with clocks in circular motion show that time dilation depends only on speed, not on acceleration. A clock moving in a circle at constant speed, and therefore constantly accelerating toward the center, still shows time dilation proportional to its speed. Similarly, If you accelerate a clock to a certain speed and then let it coast, the time dilation during the coasting phase depends only on that speed, not on how it got there. The correct statement is this: acceleration is what breaks the symmetry between the twins. It is why one twin changes reference frames and the other does not. But the actual amount of time dilation depends on the relative speed during the journey, not on the acceleration itself. So what is the twin paradox? It is the apparent contradiction that arises when you forget that the twins are not in symmetric situations. One twin accelerates and changes reference frames. The other does not. When you account for this asymmetry, the paradox disappears. The traveling twin really does return younger. And experiments with atomic clocks and subatomic particles have proven it. That is the twin paradox, properly explained. Thanks for watching, and hit subscribe for more deep dives into the physics that shapes our universe.